In this session, we will see how we are calculating the efficiency and regulation from the open circuit test data and short circuit test data. In the last session, it is not able to derive the equivalent resistance and reactance of the transformer from the short circuit test data. We will brush up that particular how we are calculating R equivalent and X equivalent from the short circuit data. Then we will calculate the efficiency and regulation of the transformer. We already know that to carry out the short circuit test, LV side of the transformer is short circuited, the meters are connected in the HV side, so that the current which is injecting to the transformer under short circuit test should be as less as possible. We know that the high voltage side, voltage is more, current is less, that is why we are connecting all our meters in the HV side and LV side is short circuited. The circuit setup also we have discussed. There is a transformer and auto transformer. From the auto transformer, we are giving supply to the HV side of the transformer. In this case, because it is a short circuit test, ammeter, wattmeters, okay, then potential coil, and the voltmeter and short circuit. You are short circuiting the secondary of the transformer. That is, in this case, is LV side. And all our meters they are connected in HV side of the transformer, and we have to inject the current such that the full load rated current should be flow. For very small voltage we are getting the large current because it is under short circuit test. Therefore, what I am doing from the single phase supply, I am giving a supply here and I am adjusting this the thermostat voltage output voltage so that for very small voltage we are getting a rated current. Then see that ISC should be corresponding to the rated current because it is ISC I am representing because it is short circuit. Therefore, ISC is corresponding to the full load current and corresponding value of the voltage and the wattmeter readings that are not on, that is the WSC. In this case, the losses, because the voltage applied is very small, and then the core losses which is contributing from this wattmeter is very small. Therefore, what we are assuming that the whole wattmeter reading under short circuit test gives the copper losses in the transformer. Therefore, how we are calculating the parameters that we will see now. From the test data, series equivalent, that is equivalent resistance, because you are all over connected the meters in the HV side. Therefore, I am representing this as R equivalent refer to the HV side, X equivalent refer to the HV side. What I am calculating here. Then also we know that the wattmeter reading gives the full load copper loss of the transformer under short circuit test. Therefore, to calculate the value of the resistance, we know that W is equal to I square into R. The copper loss, usually how we are expressing W is equal to I square into R. Here W is WSC, R means it is R equivalent, that is referred to the HV side. Therefore, using that formula, what I am getting here is R equivalent is equal to the total copper loss divided by ISC. Just I am using W is equal to I square R. That is the formula. Therefore, R is equal to W by I square. The same formula is used here, WSC by ISC square. Then the formula for the impedance is it is a ratio of voltage by current. Then voltage applied under short circuit test is VSC, and the corresponding the short circuit current that is corresponding to the rated current of the transformer is VSC by ISC. That is voltage by current gives the impedance, then power divided by current square gives the resistance. That is resistance referred to the equivalent resistance referred to the HV side, impedance referred to the HV side. If you know the resistance and the impedance of the circuit, then the reactance can be calculated as it is the square root of impedance square minus resistance square, that is Z equivalent square minus R equivalent square. This is how you are calculating the value of R equivalent referred to the HV side, X equivalent referred to the HV side. Suppose if you are interested to transfer this X equivalent R equivalent from the HV side to LV side, from one winding to another winding. In this case, it is treated HV side as a primary, the LV side as a secondary. Therefore, X equivalent, the LV side, that is secondary, is equal to X equivalent of HV, that is the primary reactance by the transformation ratio square. Similarly, R equivalent refer to the secondary side or LV side is equal to R equivalent of HV side divided by K square. Means this is how we are calculating the equivalent resistance and the reactance of any side, either HV side or the LV side. It is quite evident from this diagram. This is a VSC, this is a ISC. Combination of R equivalent and X equivalent is nothing but your impedance. Therefore, how to get the impedance? It is voltage divided by the current. And the total power loss in this case is ISC is for R equivalent, that is given by WSC. Therefore, R equivalent is equal to the power W divided by ISC square. The same formula I am using here to calculate the value of R equivalent and Z equivalent. Then the efficiency of the transformer you are given, that is, we know that the efficiency of the transformer is defined as it is a ratio of the output power to the input power, or in other words, it is the output power divided by the input can be expressed as output plus here there are two losses. One is the core loss, the another one is the copper loss. That is, the efficiency of the transformer can be expressed as the output divided by output plus core loss plus the copper loss. Here the copper loss can be expressed depending upon the loading of the transformer. That is, if it is a full load, the copper loss is corresponding to full load copper loss. If we are loading for half of full load, then the copper loss corresponding to half the load. Then how to calculate these things, that we'll see now. Here there are two types of losses. One is called as a core loss, the other one is the copper loss. These losses are wasted as in the form of a heat. Because of that, there is a rise in the temperature of the transformer. That is why the transformer is kept in a transformer tank consists of transformer I for the purpose of cooling. Therefore, output power of the transformer will always be less than the input power. If the losses are there in the transformer, definitely the output power is less than the input power. Therefore, the efficiency can be expressed as output power divided by output power plus losses. Here there are two losses, that is why I am elaborating here in this next expression. It is output power as it is, the input power is output power plus the losses as two component, core loss and the copper loss. That is, efficiency is output divided by input, that is nothing but output power plus core loss plus copper loss. Then we will look into for a different loading condition how to calculate the efficiency of the transformer. Okay, we have seen that from the no load to full load, the condition, the core loss remains a constant. Irrespective of the load condition, the core loss remains the constant because the core loss is depending upon the applied voltage. Because you are applying the rated voltage, the transformer primary winding, therefore you are not varying the voltage applied to the transformer. Therefore, the core losses remains the constant. It is not depending upon the what type of load, how much load it is putting on the transformer. Irrespective of the load condition, core loss or the no load loss remains the constant. On the other hand, we know that the winding current depends upon the degree of loading. However, the copper loss is nothing but I square R loss. The value of the current I drawn by the transformer or delivering to the load of the load is depending upon the factor of loading of the transformer. If it is a more load, it is drawing a more current from the supply. Also, it is delivering the more current. Then the copper loss, the basically depending upon the current. Therefore, if the current is drawing from the transformer is more, it is a more copper loss. Therefore, we have to generalize the equation for the transformer efficiency like this. We know that the transformer is rated in terms of kilovolt amperes, or a bigger unit is MVA, megavolt amperes. It is not expressed in terms of watts because the output of the transformer is depending upon the type of the load, either it is a lagging load or a leading load or unity power or factor load. It is depending upon the power factor of the output is depending upon the power factor of the load. Therefore, the transformer is always rated in terms of volt ampere. Either it is a kVA or it may be expressed in the MVA. Okay, we'll consider here if the transformer is expressed in terms of kilovolt amperes rating of the transformer, it is represented by S. The S is in terms of kilovolt ampere. Now, the x I am using a letter for a degree of a loading means x is equal to 1 means x is equal to 1 means it is a full load. X is equal to half, it is called as a half full load. If it is x is equal to 3/4 means the load is 3/4 full. That is, it gives the degree of the loading, that is x. Okay, for a different loading, the x is equal to 1 for full load, x is equal to half for full load, x is equal to 3/4 or 3/4 full load, or if it is 60% of load, it is a 0.6 times x, and so on. Therefore, the transformer is delivering the under the x load condition. X load condition. For example, I am taking 80% of the load. For example, S is my 100 kVA. It is 100 kVA. For 80% of the load, my transformer is delivering only 800 kVA. Sorry, 80 kVA. If S is 100, if loading factor is 80%, that is 0.8, then at that instant of time, the output of the transformer is 80 kilovolt ampere. Suppose if the power factor is 0.8, then what is our cos phi is equal to 0.8, then what is my output power in kilowatt? That is a kVA multiplied by power factor, or volt ampere multiplied by the power factor gives the watts. You can see that is active power, reactive power and apparent power. If we are multiplying the cos phi to the apparent power, that gives the watts. If you are multiplying sin phi to the apparent power, that gives the reactive power. Here, the output of the transformer is x into s into cos phi. For example, power factor is 0.8 means my output power in kilowatt is, that is s is, that is x is 0.8, s is 100 and cos phi is 0.8. That is what we are getting here. It is 80, that is 80 into 0.8. 80% of, that is 6.4 kilowatt. That is the output of the transformer is 6.4 kilowatt. This is how we have to find out the output of transformer. In general, equation for output of the transformer is the loading factor multiplied by the rating of the transformer multiplied by the power factor of the load. That is, you have to remember that the output of the transformer is given by, it is the loading factor multiplied by the kVA rating of the transformer multiplied by the power factor of the load. Then the next important the factor what you have to calculate is the copper loss of the transformer. We know that the copper loss at full load is, it is represented by x is equal to 1. Therefore, let the copper loss at full load is WCU FL. It is represented by WCU FL. It is corresponding to the full load copper loss. It is corresponding to copper loss. Therefore, the copper loss at any loading condition x, that can be written as x square times copper loss at full load. I will give a small example. If the current is 2 amperes, if the resistance is 1 ohm, then the total loss I square R loss is 2 into 1, that is equal to 2 watts. Now my loading is decreased from half the load. The full load is 2 amperes. Now I am reducing that to 1. Then what we are getting? The current is now, it is 1. The resistance is 1. Therefore, in a previous case it is 2 square into 1, that is 4 into 1, that is a 4 watts. That is 2 square into 1, that is equal to 4 watts is the copper loss at full load. Now current is reduced by half from 2 amperes to 1 amperes. Then what is the copper loss at half load? That is 1 square into 1. That is 1 square into 1 is 1 watt. Full load copper loss is 4, whereas the copper loss at half load is 1 watt. Means if the current is reduced by half, whereas the copper loss is reduced by 1/4 times, that is square of the loading factor. It is the copper loss is reduced by square of the loading factor. That is why I am written here. Therefore, the copper loss at any load x can be written as x square times copper loss at the full load. This is very important factor that you have to remember. Therefore, the constant loss is given by, it is Wi. The constant loss is Wi. Irrespective of the loading condition, the copper loss remains the constant. Therefore, I have written here two different equations for depending upon the how we are taking the units of the different parameters in this equation. That is, now the equation for our efficiency is output divided by output power plus core loss plus the copper loss. Therefore, I am putting here the output is x into s into power factor, that is the output, that is the loading factor multiplied by kVA rating multiplied by power factor, that gives the output of the transformer. Then it is the output of the transformer, it is same as the numerator. Then iron loss remains a constant, iron loss remains a constant irrespective of loading condition. However, for different loads you have got a different copper loss. Therefore, the copper loss at any load is equal to x square times copper loss at full load. X square times copper loss at the full load. Here S is taken as a kVA. Therefore, your iron loss as well as the copper loss also should be in terms of kilowatt, and you have to apply this expression. The iron loss and copper loss is given in terms of watts, that you have to convert it a kilowatt and you have to substitute in this expression. Otherwise, a simple equation you have to make use of this formula inversely, so that it is x into s you can express in terms of watts only. It is s is in terms of kVA. To convert it to volt ampere you have to multiply 10 raised to 3 into cos phi. This is the watts. Therefore, it is a loading factor multiplied by kVA rating of the transformer multiplied 10 raised to 3 into power factor. Similarly, this is the output, and iron loss is also in terms of watts. The copper loss is also in terms of watt. It is x square times copper loss. This is how you have to make use of the formula, and you have to calculate the efficiency of the transformer. Here, the Wi is you are getting from the open circuit test data. WCFL you are getting from the short circuit data. Then any load, either it may 0.8, 0.9 or unity power factor or 0.7 power factor, you can calculate. For a given load, you can calculate the efficiency by Wi and WCFL, because we know what is the rating of the transformer, and you have to, if you want to determine the efficiency at any load, you can put corresponding value of x and corresponding value of the load, and Wi and WCFL we are getting from the OC and SC test. This is how you have to calculate the efficiency of the transformer.